So welcome everyone. So in today's session, we will go through the process of setting up the Tanner tool and to understanding its user interface and how to load the standard libraries and how to create a new design in the SEDit. So by the end of this lecture, you should be able to create your own first schematic using this Tanner tool. Okay, so let's get started. So once the Tanner tool is installed, once the Tanner tool is installed in your system, so all necessary files will be available in this example folder, right? So in the previous session, we created a folder name with the example. So in this folder, we stored the all the required license files and all the guidelines files, right? So this example folder will be available in the Tanner tool installed libraries, right? So once the Tanner tool is installed, all the necessary files will be available in this example folder. So including the license, examples, and guidelines and user guide. And in this process folder, you will find all the standard libraries over here. So these components are loaded automatically into the respective folders. So during the installation process, so this means you don't have to manually download or you need to again install anything extra after the installation. Okay, so this example folder includes sample projects. So here you will find a folder with name designs, right? So here you will find some sample project so that you can explore. So these examples are great for the understanding how different circuits are designed and simulated. So in this process folder, you will find some standard libraries. So these standard libraries contain components such as transistors, diodes, and other devices. So these components that you will need for your designs. So these libraries are loaded and ready for use. So when you need a specific component like diode or transistors or MOSFETs, so you can simply select it from the standard libraries. Okay. So now let's begin with an overview of the SEDit interface. So for that, just to open this SEDit, just to give a double click on it, so it will open. So when you first to open SEDit, so this interface consists of different parts like main menu, so workspace. So this is the workspace. So this is the main menu. So at the top of the window, we have the main menu. So it contains several drop downs such as file, edit, view, draw, cell, setup. So like this. So these tools provide access to the all major functionalities for design, simulation, and configuration. So when coming to the workspace, so in the center of the screen, we have the workspace. So, and we can also call it as canvas. So this is where your schematic will be built. So you can place components, wires, and symbols here to form your circuit. Okay. So next, component browser. So to the left of your workspace, you will find the component browser here. So this is the component browser. So this section allows you to easily access various components like transistors, resistors, and like voltage sources and etc. So it's organized into different libraries, so making it easier to locate specific elements for your design. So next, on the right side, there is a design navigator. So this is where you can see the hierarchical view of your design. It will show you the relationship between the different blocks or schematics. So it is especially useful when you are working on large or complex designs. Okay, so now let's move to the toolbar. So this is toolbar here. So this toolbar, which is just located just below the main menu. So this is the main menu. So under the main menu, you will find this toolbar. Okay. So the toolbar offers a quick access to the frequently used tools. So making it easier to perform the actions without dividing the deep into the menus. Okay, so here you will find the options like new, save, new design, open design, and save, options like that. These first set of icons are the basic file management tools. These are used to open a new file or to save, and it will also give us the save as option also. So there are standard tools for creating, opening, and saving your schematic designs. So these are the standard tools for creating and opening and to save your schematic designs. So here you will find an undo and redo buttons. So we have the undo and redo buttons here. So these allows you to revert or reapply the recent actions. A handy feature so when making the frequent changes. So next, a label tool. So you can, by using this tool, you can add text or labels to your design using the text tool. We can also call this as label tool. So this is useful for annotating your schematics and making it easier for others to understand. Okay. So lastly, so here we are having the simulation tools. These are the simulation tools. So this is for set up the simulation and this is for to start the simulation. So these icons allows you to set up simulations and define sources and run your simulation directly from the SLA. So these will be important when you move from design to simulation. Okay. So now let's walk through the process of creating new design in the Tanner tool. So now I will tell you how to create a new design in the Tanner Edit. Okay. So to create a new design in the Tanner Edit, so go to the file menu here. So just click on it and select a new design here. So now you will be prompted to give your project a name and you specify where you want to save it. So here I am giving a project name like Inverter. So here you need to choose a directory. So you can choose any drive or any folder to store your project. So in my case, I will be saving it in D drive. So in this D drive, I have already created a folder for these designs. So that folder name is Panel Designs. So in that folder, I'm going to save this project or save this design. Okay. So I'm just clicking. Okay. So after giving a design name and after defining the folder where you want to store this design, so just click on OK. So this will create a new project folder with your design inside it. Okay. So here you will find this new design over here. After creating the new design, so now we need to add the components, right? So for that we need to add the standard libraries. So how we will add the standard libraries? So that I will tell you now. So under this newly created project, so you will see a section for the libraries, right? So this is the section for the libraries. So by clicking this add, so you can add a new standard libraries to your project. So for example, if you need a MOSFET or a transistor to add into your design, so you can find these components in the standard libraries under the device folder. So simply select that component. Okay. Now I am going to add the standard libraries. So just browse here and you need to select where your standard libraries are installed. So here in my Tanner tools, we have already created an examples folder, right? In this folder, we will find all the required standard libraries. So here go to the process folder. So here you will find some standard libraries. So regarding for 250 nm technology. So here I am going to choose this generic 250 nm standard libraries. So and if we want to add MOSFET and transistors into our design, so we need to select this generic 250 nm devices. So just give a double click on it. So here you will find an SEDIT file with the name generic 250 nm devices. So you need to select this file and just click on the open. Again click on OK here. So now the standard libraries regarding the devices are loaded into your project. So if you give a double click on this generic 250nm devices, so here you will find the different components which are available in these devices libraries. Okay. So like PMOS, NMOS. So after adding the devices libraries, now we need to add few more libraries like this, like spice command, spice element. So we need to add all those libraries. And for all those libraries, so here again in this process folder, just scroll down a little bit. Just scroll down a little bit. So here under you will find the standard libraries. So here you will find a standard libraries folder over here. So just give a double click on it. So here you will find a MISC folder. So again select this MISC edit file and again click on open and click on OK finally. Now MISC is also added. Now repeat the same process for to add the spice command, spice elements. Okay. So next I'm selecting the spice command. So choosing this file. So open and again click on OK. Now spice commands also added. And finally I'm going to add spice elements. So open. Okay. So now to design an inverter, so all the required libraries are added to my device. So after adding the libraries, now we need to create a new cell for our inverter design. So in the main menu, so go to the cell. So here select the option new view. So here you need to define a name for your new cell. So I'm giving like, so CMOS inverter. So this is my cell name and here you need to select the view type. So since we are working on a schematic design, so choose the schematic cell as the cell type and confirm the section by clicking OK here. Okay. So one more point is here, so we can't give spaces in the cell name. So the cell name can't contain any spaces in between any words. So I just replace the space with the underscore symbol. So after modifying the cell name, just click on OK. So now we have a new cell over here. Now let's start adding the components to make the inverter schematic. By using the plus and minus symbols on your keyboard, you can zoom in or you can zoom out your cell view. Okay. So now we have the new cell. So now we will create a inverter schematic over here. So this is the workspace. So here we will create the schematics. Okay. So to create the schematic for an inverter, so as we know, we need a one PMOS and one NMOS, right? So if you want to add a PMOS, for instance, so select the devices library. So this is the generic 250nm devices library we have here. So under this, please select this PMOS. So just hold it and move it to the workspace. So and place it in the workspace wherever you want. So just give a click on here. So it will place the component in the workplace. So you can add as many as PMOS as you need by simply clicking to place additional instances. Okay. Like this, you can add as many as PMOSs to your design. Here I just need only one PMOS. So that's why I'm just undoing it. So after placing the required number of transistors. So you can just click on escape. Okay. So now we need to place an NMOS, right? Now select the NMOS, hold it and drag it over to the workspace and place it wherever you want, and again click on escape. So once the PMOS and NMOS are placed, so now you can connect them using the wire tool. So here in this tool section, here we will find a tool with the name wire, right? So simply click on the component terminal and drag to connecting the points of the other components. So here I am just connecting the 2 points of PMOS and NMOS. So just give a click. So after that, so we need to connect So after placing and connecting your components, now we need to connect a VDD and a ground for this circuit. So to add the VDD and ground, so we need to go for the MISC folder. So under this MISC folder, we will find so VDD and ground. So first select VDD and drag it to into your workspace. So just connect it over here. So to escape this, click on the escape. So after that, just select the ground and drag it and connect it over here. Again click on escape. So now we have connected the VDD and ground to our circuit. So now we need to define the input and output ports for your circuit. So for that, so in the toolbar, so here you will find the different ports like input port, output port, in out like this. Okay. So here I am selecting the input port to define the input for this inverter circuit, and I'm just connecting it over here. So here you can define a name for your input port. So I'm just leaving it as in. So if you want, you can change the font size of your input port also. So I am just leaving it as it is and just click on OK. So now input port is connected. So now we need to add the output port and select the output port from the toolbar. And we need to connect this output port over here. Okay. So if you want, you can change the name and font size of your port names. Okay. Now we need to specify the input sources. So here we need to give an input source, right? So here we need to specify the input sources such as voltage sources or current sources. So by selecting them from these spice elements. So if we want to add the input sources, so those input sources will be available in this spice element folder. So if you scroll down a little bit here under, you will find this voltage source option. So make sure you have a power supply connected to your circuit. So that is DC source. So if we want to add the voltage source for your input, so generally for transient analysis, so we typically use a pulse input voltage to test how the circuit reacts to the changing in input signals. So to add the input source for this circuit, so go to the spice elements folder. So under this folder, you will find an element with the name voltage source. So here you will find the schematic of different input voltage sources. So if you click here, so it will change, it will show you the different voltage sources which are available in the Tanner study. So here I am just selecting a pulse input voltage. So why I am selecting this pulse input voltage means, so for generally for the transient analysis, we typically use a pulse input voltage to test the circuit. Okay. So after selecting this particular pulse voltage source, just drag this voltage source over here. So I am just placing it in the workplace. So if the element is showing like this, so just click on escape. So it will went off. So now, so this is the pulse voltage signal for the input port, right? So I am just copying this input port and I am just connecting this input port to this pulse voltage source. So after that, so here we need to connect the ground. So just copy this ground. So you can use like Control C and Control V buttons to copy and to place the ground. So after placing the ground, so now we connected a pulse voltage source to the input signal, and now we need to give a DC input voltage source this power source. Okay, so here we connected VDD, right? So this VDD is nothing but the power source to this circuit. So now we need to choose a DC source. So again select this voltage source, and here you need to select this DC source. Just drag this DC source into your workspace. So just drag this voltage source and place it so wherever you want in this workplace. So this DC voltage source we need to give for the VDD. So just copy this VDD and just connect it over here. And here we need to connect the ground again. So if you just give a double click on this pulse voltage source, so here you can find a properties tab. So in this properties tab, so if you want, you can change the parameters or the properties of these voltage sources. So here, if you want, you can change the pattern also. Here I am giving the pattern like 101010 for the input port. Or if you want, so you can change the voltage levels also. So now I want to change this VDD voltage to from 5 volts to 2.5 volts. So here I want to give a 2.5 volts to the VDD. So like this, you can edit your properties of your voltage sources. So after editing, so just click on save. So just click on the save button here. So here this pulse source will create a square wave signal. So this square wave signal is suitable for testing digital circuits like inverters, like that. Okay, now the circuit is completed. So now we need to simulate this circuit. Okay, so before doing the simulation, first we need to set up the simulation. So for that, so just go to this simulation. So set up simulation option here. Just click on it. So here you will find the different analysis options over here. So in these different options, so just select the transient analysis over here. So in this transient analysis, we need to set a key parameters for this transient analysis. So here we need to define the stop time. So the stop time refers to the duration for which the simulation will run. So here I am just giving like 100 nanoseconds. So this is my stop time. So here the second option is maximum time step. So you can leave this on automatic or you can specify a time step. So here I am giving a time step like 10 nanoseconds for more precise control. Okay. So after that, we need to go to this general option here. So in this general option, so here we need to add the libraries over here. So how to add the library files? So default, it should be the empty, right? So I'm going to add the libraries files. So go to the browse option here. So here we need to add the library file. So go to the standard library option, which is available in this process folder. So just select this generic 250nm folder. Here you will find a generic 250nm text file, right? So just open it. So in this folder, you will find the generic 250nm library file, right? So just select this file, and click on open. So after choosing the library, so go to the end of this line. So after reaching the end of this line, so after the lib, so you need to give a space here and you need to enter t double time. So here you need to give one space and you need to enter the t 2 times here. So after giving the space and entering the tt, so just click on OK. So don't forget to give the space and tt over here. So after giving the space and tt, so just click on OK. Now the simulation setup is ready. Now I am going to explore. So where the input and output waveforms has been displayed in the graph. So to print the input and output waveforms in the W edit. So for that here we need to use some commands in the circuit. So for that, so go to the spice command folder or spice command library. So here you will find an option like print voltage. So in this print voltage, you will find different options for print 12-bit, print 4-bit, print 8-bit, print AC magnitude voltage. Like this you will find. So among these options, you need to select the print voltage. So you need just select this print voltage. So please make sure. So you need to select the print voltage over here and then drag it to your workplace. So to rotate or to change the direction of the components, so you can use the R letter in your keyboard. Okay. So after selecting the print voltage, so you can place this print voltage probe at the key points in your circuit, such as input and output nodes. So here I want to just observe the waveforms for the input and output. So for that, I am just placing these probes at the input and output. So after placing the probes, so just save the circuit. So you can place these print voltage commands wherever you want. Like if you want to print the VDD voltage, so you can also place this print voltage over here also. So you can place wherever you want to observe the signal. So we can place the print voltage over there. Okay. So now to simulate the circuit, so just go to here. So here you will find the option for start simulation. So just click the run simulation button from the toolbar. So now the simulation will start. Now the simulation will start running and the transient analysis for the specified time. So here, so the waveforms will be opened in the W edit. So here if you observe, the input and outputs are combined. And if you want to separate, so you can select the option here. So put selected traces on separate plots. So just select this option. Now my input and output waveforms are separated. So if you observe here, so if the input is 1, the output is 0. So if the input is 0, the output is 1. So this is the required output for an inverter, right? So for an inverter, the output should switch in response to the change in the input. So by setting up a transient analysis in SEDIT, so it will allows us to evaluate the time domain. So this is the time domain behavior of your circuit. So by using the pulse sorts, so we have given the pulse pattern like 1010, right? So by using the pulse sorts and running the transient simulation, so you can observe how the output responds to the change in the input signal over time. Okay. So this is critical for validating the functionality of digital circuits like inverters or other timing sensitive designs. Okay. So with this, So by using the Tanner essay edit, we successfully created an inverter design, and we successfully plotted the input and output waveforms also. So thank you everyone.